Okay. So this is going to be about StatMech and a couple other pieces. So, every time I look around to see if someone's got a better, like, little online model thing that's doing a good job, but I wasn't really sure if I found one for percolation. But let's talk about this a little bit. So StatMech, statistical mechanics. So it's an oxymoron, right? It's very weird. This is something that was created at the end of the 1800s, I think the term comes into being. But it's this idea that instead of, we're thinking about all the atoms in this room, there's this sense from the mechanical age, and certainly the great success of all of these theories of mechanical machines and so on, that, well, what you'd really want, right, is the exact path of this little molecule, and it hits this one and bounces off, and it's like a huge thing of billiards, really hard, right? That's kind of what people were used to thinking about doing, though. So that's obviously impossible, right? Too many things. And then this notion of statistical mechanics, we'll do things kind of on average. We'll imagine, roughly how things are working and give them distributions and so on, right? And that was, looking back to that Einstein 1905 paper, was that's, this cornerstone in us getting to knowing atoms exist, understanding atoms exist as the Gaussian distributions, random walks, talked about these things. Okay, so statistical mechanics. So, right, how can you have probabilistic mechanical systems? Well, you absolutely can. So, in the way we model them. Chaos is a different thing. Okay, so percolation. So this is a really simple idea. So and you could really easily simulate this for yourself, right? You just make a matrix in whatever code or software system you use, and then just with a coin go to each one and weighted coin, right? So with probability P, you make it white, and probably 1 minus P, you make it black. And then the idea is that these white ones are kind of like open pores. This is like closed-in material. You can think of it like that. And then the question is, if you start over here and you want to run through to the other side, right? Can you do it? So in this case, no, right? There's no connected way of getting through here. You're not allowed to hop. You imagine this is like a little cave structure or something. And the notion is percolation, right? Which percolating through the ground. There's also coffee, which made scientists happy to talk about this, right? But the idea is, can a liquid flow through it? So there's a toy model for that sort of problem. So a lot of the motivation for this came from oil companies originally, I think, they got excited about this because they wanted to get things out of the ground. I guess eventually I gave up and just went to fracking, just blow it up. Fracking makes this happen, right? So this is where we've dialed P up, if you like, and this probability they're all uncorrelated, right? There's no connection from pore to pore in terms of whether it's open or closed. You just flip a coin at each time. So this is a case where, yeah, you can walk through it. So obviously for P equals 0, it's all dark. There's no way you can get through it. For P equals 1, this is all open, so you can walk straight through it. So what happens in between, and what does the structure look like? If you think about this, lift this off and think about this as being a network, and you start to think of these people being they're infected or not infected, or you can think about edges as well, right? So it's really the connection between them being open or not. So you could flip the coins on each of these things. Is there a doorway here or not, right? And then of course you have different lattices. And then you might think this is a universality problem. Well, maybe the details don't matter, right? That would be a nice, you don't know what's going to happen, but that would be a nice kind of thing, right? We love that sort of stuff. It doesn't matter if it's hexagonal or like some other funny kind of lattice that maybe isn't regular. But it turns out it does matter. So that's, let me show you that. Don't think I have a simulation for it. Yeah, nope. Yeah, so percolation threshold. So the percolation threshold, that's the value of P for which you just start to get a connected component that allows you to walk from one side to the other. We'll have various terms for that, but giant component is often used, or the giant cluster, a percolating component, right? So you can see there's a list of these things, lots of different kinds of grids, lots of different values, right? So these are site percolation and bond percolation. So that's the links. This is the door thing, right? Whether you put a door at the side of each square, and site, whether you're allowed to go through it or not. So in a sense, all the doors are open around a site. It's just whether you can go through it. And so they have different values, and you can see people have worked out all sorts of madness to like ridiculous numbers of decimal places and got really carried away. So that's great. But the thing is, there isn't a universal piece here. That really depends, in detail. We'll come to this later on in the course, because towards the end when I talk about some other universal pieces. But macroscopically, if you simulate things on grids, then you can see that grid at a large scale, depending on what your simulation is, but you can kind of see it, right? If you simulate things on hexagonal lattices, then you can't see the hexagonal lattice. If it's a big enough thing and you step far enough away from it, you can't see that grain. There's no grain of a hexagonal lattice. And in fact, if you make a hexagonal lattice and kind of squeeze it like this, do stress and strain, it feels like a solid. There isn't a sort of, but if you get one of these together, you can do this and you say, oh yeah, there's some weird thing there's some microstructure in here that's not, that doesn't appear to be like a continuous solid. That's something for later on, but hexagonal things are pretty spectacular. All right, so this is a simple thing to play around with. What else do I have here? So easy to simulate. The one tricky piece for this is, for example, so let's say we come to this one and we want to count up all the connected components. Sometimes these things are built into whatever you're using, MATLAB or Python. You could find someone's made a package of it, but it's not a bad problem to think about for yourself, right? So you'd start here. This isn't part of an open pore, so you just give up, and you kind of march across and you find this one is open, and you say you've visited all of these, and then you look at all its neighbors and see that it's closed, and so you'd mark this as kind of group 1. You could do that. And then go across, you mark this as group 2, it's not connected to anything else. And then maybe when you get to here, this is group, whatever it is, 7 or 8, you just put a 7 here, this is already visited, so this is a 7, 7, 7, 7. So this is, you'd see this, right? You could do something like this. And then you'd have all these labeled groups and with sizes, and then you could plot a histogram of them. And what happens is, before you get a giant connected component, you kind of have the sharp decay in size. But just as you get to this point between these two cases where there's a percolating component and there's not one, as you get to which is the critical point or the percolating threshold, you get a power law size distribution of, yes, you do, power law size distribution of these little blocks. Just on that cusp, right? So we'll come back to this for robustness. That got a lot of people excited. This is called the critical point. This is, right, it's the same sort of thing with ice forming. You kind of get these bigger, lots of little pieces, some number of smaller pieces that are a bit bigger than that, and so on, so on, so on, and then a big piece, and eventually it makes one big giant component. So that's fun. And then so the idea is that, oh, maybe lots of real systems with these power law size distribution things, they're somehow like this, but they're being forced back to this threshold. Something in the world is making them go to that threshold. People get very excited about it. They call it the edge of chaos, or the term that popped up was self-organized criticality, and we'll come back to that later on. But the idea was, again, this word self-organization, there's nothing dictating it. There's no big lever that's pushing it, from outside that's pushing it this way into this percolating point, or this critical point, percolating threshold. But somehow it comes about. And I don't know, there are there's a lot of debate about that, but we'll see what we talk about here. All right, so this is a different thing. This comes out of the 30s, and it was just a PhD student, I believe, Ising. In Germany, just came up with this ridiculous model for magnets, right? So this is a joke magnet. It's a toy model, and let's try it and see what happens, right? So you've got, and they could be all sorts of things, right? So this is upspin and downspin. So that's the idea. We want to see if our magnet goes this way or that way, or has nothing going on at all. And we're going to make, in this case, it's a 1D one, and then we can have a grid version. You can have all sorts of things. You can have a 3D version if you want. Just each point on the lattice has a little tiny magnet itself, right? So this is a bit of a, I guess, a MIMO, magnet in, magnet out situation. So that's cheating a bit, but we do know that these little characters have spins, right? Homunculus, it's the homunculus approach, right? Okay, right. Magnets inside magnets. All right, so that's the idea, though. There's a little local spin, and you can just add them all up, right? And so you'll see from this is a beautifully developed world of theory and models and so on, and then eventually computers came along and tremendous excitement. People say, well, what if this was voting, right? What if this is voting? So there are lots of parallel things that are inspired by the Ising model. It's a kernel of a great amount of development. These people are neighbors. They could be on a network. They see their friends voting or whatever, and yeah. So, and some of that stuff is just it's not really right to do some of it. They get a little carried away. But anyway, this is the kind of thing you see. So there's an overall temperature that this thing is bathed in, and that's making these things jump up and down potentially, right? So if it's really really high temperature, then they're being affected. There's a lot of thermal sort of noise that's pushing these things. They're just jumping around, and they can't really care too much about their neighbors, right? But as you lower the temperature, there's a natural coupling, right? Like magnets like to line up with each other, so there's a natural coupling that comes about, and so they start, and depending on how you connect them up, so it's all just sort of four neighbors. So in this case, this one here is not happy, right? Because its two neighbors are pointing the opposite way. This one is, this is okay, this is a bad one, this is a bad one, this is a bad one. So this is a frustrated one, if you like. And you can have all sorts of things where, they can or can't move, and you talk about spin glasses and frustrated systems and so on. All right, so what happens with these, and again, it matters, the grid matters to some extent and so on, but as you lower the temperature and you have your little model here, then eventually they can get connected enough with each other or care enough about each other, right? There are these sort of two things pushing them, and there'll be one side which will be favored, and so the macroscopic magnetism of this system will go in one direction, either pointing up or pointing down, because the ups win or the downs win a little bit. And let's see if I can run a little simulation of that. But it depends where you start, right? So you could start here and then heat it up, and then by this point it's all just static. As you cool it down, it could go to here. This is maybe an initial point at a particular temperature. It would quickly go to this point, right? So you start it with it being maybe completely messed up, it would jump. So this is a phase transition story. Very important thing for systems. It's a phase transition, right? These are really different phases. This is like gas and water. They're different things. You can have hotter and hotter gas and colder water. Eventually you hit another threshold, but they are of the same phase. So there is a real transition point there. And often in these systems, it will depend on, as you hit here, there's going to be some growth away from this. How sudden is this, right? It could be a sort of a smooth thing, or it could be disjoint. We talk about how explosive those points are. Okay, so the Drosophila, right? It's the fruit fly of StatMech. Everyone loves the Ising model. Right, power law size distributions at the critical point. Now, of course, it's just this one point, so that's a kind of a knock against it being accessible. So here's a little example. I think I can just, so it's all messed up. It's got, let's make the temperature kind of high. So this is just going to bubble, right? They're trying to, they would like to be the same as their neighbors, these little magnets, but the temperature is pushing them around. And so as soon as you drop the temperature down enough, then they start to coalesce, and you'll see, like, right, this is going to get eaten up, went away, and that's going to happen. This will, because it's on the edges, right, because it's rounded a little bit, on average you're going to be exposed a little bit more to people who aren't like you, right? And so you will, ooh, it has a weird hand. And peninsulas are dangerous, right? This is not going to work out. That one's going to get, it's going to be dangerous at the end. It's going to eat back onto it. Chomp, chomp, chomp. There was a paper in Science a few years ago that claimed that this was a thing that leads to instabilities in regions for countries, right? So if you have a peninsula of a country going to something else, then that's a bad thing, right? And I don't know if that held up, but it's definitely an appealing thing. It's like, okay, right? Sort of makes sense. Anyway, so that will get eaten up, and of course, as you can just destroy it again. You get to the critical temperature, which is 2.0 what is it, 2.2? Sort of hold apart, yeah, and then it's gone. So you can see this is a very simple model. There is this big outside thing, this temperature, right? There is one big piece from outside, it's true, that everyone experiences. And that could be, so you can see how people are going to take this in all sorts of directions, like voting, there's some temperature, some ambient background kind of disposition of your state or your country or whatever it is, and you have some randomness on top. So local plus global. All right, that's good. Gosh, you can do all sorts of things with this. Yep. Okay, craziness. Ooh, let's make it bigger. That's harder. All right. Right. But it is, right, it is, you can see this will take a long time for itself to kind of, for all of those things to fight. It started as even, right? 50-50 basically. Once it's all random, it's 50-50. So coming back, depending how quickly you pull the temperature down, it's going to take a while for this thing to sort itself out. All right. Okay, that's a thing.